All right, we're going to kick things off. We want to welcome you to amine-based gas sweetening part 2 with Mike Sheelan from Amine Experts. A little bit of history on GPAC. GPAC is a nonprofit organization whose goal is to promote the interaction and exchange of ideas and technology to those involved in the hydrocarbon processing industry. GPAC has operated in Alberta since 1959 because of the support of our members and sponsors, including our gold sponsors, Equinox Engineering, Gas Liquids Engineering, Rangeland Engineering, Spartan Controls, our silver sponsors, Enerflex and Tundra Process Solutions. There's a lot of exciting events planned for 2021, including a 4-part series on hydrogen starting in a couple of weeks, as well as the always popular golf tournament in September. For more information on these, you can check out the GPAC LinkedIn page. A bit about Mike before we start. Mike is the co-founder of Amine Experts in 1999, and is currently senior principal engineer. And for 40 years, Mike has provided expert advice, training, and consulting services in the area of hydrate control, gas dehydration, gas and liquid sweetening, hydrocarbon recovery, and sulfur plant operations. For questions that you might have that pop up during the slides here, just type them into the Q&A box at the bottom of your screen, and we'll get to them at the end of the presentation. Over to you, Mike. Thanks.
Yeah, thank you, Gord. And thanks to everybody who's taken the time to attend this webinar, and thanks to GPAC for the opportunity to present it. Session 1, which we did in December, was covering the basics of amine sweetening and the amine solvent itself. And session 2 here is a little bit of an expansion on that, and it's the subject is why amine systems fail. And I have to note the co-authors for all the work that we did to put our database together. Ben Spooner, who many of you probably know, is out of our Houston office, and Philip Lagrange is out of our office in the Netherlands. So between them, not only do I have to thank them for putting the database together, but also doing the troubleshooting work where we got this database from. So just so you know, how can we develop a database like we did is the fact that we've been operating for 20 years now, and we visit lots of plants around the world, and we've done over 3,000 projects in 60 countries, and even just 2019 we did almost 300 alone. We have a large senior staff. We write a lot of papers, and we take good notes and we take good plant data, and that's how we develop the capabilities to do the work we do. So I work for the Amine Experts division of Sulfur Experts. There's also a dehydration experts group that's involved in our Canadian gas industry here. So just a quick review of session 1. We talked about the amine process itself. If you can recall, it turned 90 years old last month, and it's a process in which we take sour gas through a contacting device, and with a chemical reaction, we react the amine with the H2S and CO2 to sweeten the gas stream that comes out the top of the contactor. It's a base contacting an acid, and thus we make a weak salt solution. The salt solution we call rich amine, and that salt is regenerable, and we regenerate it in the regenerator column with steam. Heat helps to reverse that salt reaction. It drives the H2S and CO2 overhead, and that goes out with the acid gas, which can go to a sulfur recovery unit, or acid gas injection, or even flaring depending on what it is, or even venting if it's just CO2. The lean amine that comes back now is cooled, and it's free to go back into the contactor. So when we talk about some of the problems that we have, when we talk about product quality or meeting specification, we're talking about the sweet gas that exits the top of the contactor here. When we're talking about corrosion, we're obviously talking about anything in the entire process. And foaming is generally going to happen in the contactor and the regenerator. So again, we use amine treating for H2S and CO2 removal from hydrocarbon streams. We like to maximize on line time. When I first started in the industry 40 years ago, we had turnarounds every year, but now we want to run these plants 3, 4, 5 years if we can. So as we get into that 3rd, 4th, and 5th year, it's tougher and tougher to keep on stream, and it's quite challenging. Because the process is 90 years old, we've got a lot of information on it. You can Google amine and you can read till you're old and gray like me. And the problem is when you've got a problem in your plant site, what do you do? How do you try and delve into the problem and solve it as quickly as possible? The problem is there's a lot of potential root causes. It says here 60 plus. 20 years ago, in 2001, I presented a paper at GPAC called The 7 Deadly Sins of Amine Treating. And at the time I said I could have written 8 other or 7 other 7 Deadly Sins papers because there's so many things that can go wrong in an amine system. So we're going to cover some of those today. Obviously, it was daunting to talk about amine in 40 minutes. It's going to be daunting to talk about this in 40 minutes, but I'll do my best. So we have a database where we took the data from 400 separate system failures, and we analyzed them completely. Of those 400, almost 300 were ours, and then we took another 100 from the literature. And they were basically papers where we knew the author, we did a review of the work that they did and agreed that it was a well-written paper, and that's why we included it. Most of them post 1999, so it would have happened in the last 20 years, say. And these failures have a cost. They have a cost in lost production, environmental costs, maintenance, and the projects range from 100,000 all the way up to $250 million in lost revenue for the particular client. So failures can be expensive for sure. Now, we probably could have put this slide together without going through our database, just knowing what we get called to travel the world and troubleshoot on. And there's the five main ones that came up in the papers, and there's always the 3 that seem to hold court. One is corrosion, one is foaming, and the other one is product quality. And what we mean by that is, did I meet my pipeline specification? Did I meet it for H2S and or CO2? There's also some smaller sections on tower flooding or amine losses, but specifically, we're going to spend the rest of this session talking about the big 3 there: meeting spec, corrosion, and foaming. So you can gather from that then, if you can do something about controlling these 3 main subjects here, you can do a lot to controlling the downtime of your facility. If you can control your ability to meet spec, keep your corrosion to a minimum, and stop that amine from foaming, you can have a good runtime and decrease the headaches from all the operations staff, that's for sure. So as far as the way these things lined out, we did try and separate, we've got one for refineries. We do work in LNG facilities, syngas facilities, carbon capture, but this is strictly from the gas treating focus of our database. And the one on the left is processes with greater than 1,000 ppm of H2S in the feed gas, and the one on the right is less than 1,000. So we're calling the one on the right sweet gas. Now, obviously there's H2S in it, and you'd consider it sour gas, but we've just used 1,000 ppm as our limit. So on the left side, it's even with sour gas, corrosion, meeting spec, and foaming are still the big 3. And on the right-hand side, as we process more and more CO2 and less H2S, you can see that corrosion now becomes a much larger piece of the pie. 47%. So almost half of the system failures in low H2S facilities are related to CO2. The simple question that some of you might be asking is, well, why is that the case? What's the difference with high H2S versus low? And the huge reason for that is that H2S, although it corrodes steel, it does form a protective film we call iron sulfide. And as you process relatively high H2S gas, you build a nice protective film in all the equipment and piping. And over time, this reduces the corrosion potential of your system. In a CO2 environment, the CO2 or the iron carbonate doesn't form a protective film to any great extent in amine service. So the CO2 can continually attack the steel, and it tends to form pitting corrosion, which is a lot more aggressive and a lot more dangerous to operations, because we can punch holes in the side of vessels with CO2. So although we hate H2S, it's toxic, and we don't get much for our sulfur, H2S in a gas stream actually does help reduce the corrosion potential because of the ability to form this iron sulfide film. So the first one we'll cover is meeting spec or product quality. And the big question is, if you're off spec, can you afford to flare if you are off spec? Most of you can't afford to do that. You have to shut the plant in. There are jurisdictions in the world where people can get away with flaring for a short period of time or a long period of time. And the cost to you is in lost revenue, it's in environmental considerations, it's in your good neighborly pact that you made with the people around you that you will not have these flaring episodes. This particular picture is from a plant in the Middle East that I did some troubleshooting work at, and this flare went for 6 months before they called us. So they were flaring 60 million of sour gas with lots of hydrocarbons for 6 months. I liked it because that's how I found the plant. I just followed the flare. And once we solved the problem and there's no more flaring, everyone around thought the plant had shut in, but it was actually processing properly. So you really don't want to have these kind of environmental excursions. As far as H2S spec, most jurisdictions in the world, we're trying to meet less than 4 ppm, sometimes 16 ppm allowable, but with most gas processing, we're trying to reduce the H2S to extremely low levels to sell it. Now, if we want our amine to do the best job possible of meeting that tight H2S spec, there's 3 key things that we have to pay attention to. The first 2 we'll call the quality of the amine. So the quality of our treated gas is how low is that H2S spec that we're making, and the quality of the amine is the loading and the temperature of the amine that feeds the top of that tower. We want that lean amine loading, or how much residual H2S is left in that lean solution. We want that to be as low as possible for the solvent that we're using. So that means the regeneration is important. We have to drive the H2S out of that gas, out of that amine solution properly inside the regenerator column. And on the other one, the lean amine temperature, the lower the better. The cooler amine has a higher capacity to absorb acid gas, so that's a big benefit in meeting spec. And the secondary sort of knock-on benefit is that the cooler that amine temperature is, the cooler the treated gas temperature tends to be, and that means that for any downstream dehydration, the cooler gas holds less water, and that means that you're not putting such a large load on your downstream dehydration equipment. And the third and final one is an obvious one. We have to have good contact between the amine and the gas that travels up the contactor. We tend to say that H2S is equilibrium limited. The reason for that is, if you can recall from in our December session, we said that amines react instantaneously with H2S. So kinetics are not really that important. Well, they're obviously always important in a chemical reaction, but they're not limiting to us because the reaction is instantaneous. So we want good contact. The tower has to be functioning. For CO2 spec, typically pipeline spec is less than 2 mol%. If you're feeding gas to an LNG facility, we need the CO2 down less than 50 ppm, and the reason for that is CO2 freezes in the cold parts of that facility when we're liquefying the natural gas. So we need to keep CO2 out. CO2 needs cool amine, it needs good contact, it needs a well-regenerated solution, but also remember that the different types of amine react differently with CO2. Primary and secondary amines, like MEA or DEA, they react very strongly with CO2, so we tend to leave ppm ranges of CO2, so they can easily meet a pipeline spec. Tertiary amines, which is MDEA and the like, and hindered amines, things like Flexorb, they allow for slipping some of that CO2, so we can custom make our process. Now, especially with MDEA or MDA type solvents, which most of us are using nowadays, the CO2 absorption is kinetically limited. The warmer the temperature, the more CO2 reaction there is, but obviously the warmer the temperature, the less capacity the amine has. So we have to always be concerned about temperature. And we tend to say it's liquid phase dependent. H2S absorption is rapid, almost surface reaction, whereas CO2 is more bulk fluid reactivity. So it depends, CO2 removal depends a lot on how much amine I pump into that tower, or how high the weirs are in our tower to give us, higher liquid level on each tray. So we say it's liquid phase dependent. Now, what did the database tell us about meeting spec? The hugest one was high lean loading. So down here at 38 of all the opportunities, and 32 was insufficient heating cooling, which is basically the temperature. Here's the quality of the amine, the loading and the temperature. And also we've got contact. So mechanical damage and insufficient contact kind of go hand in hand. If the towers or trays are damaged, we don't get good contact. So these two are kind of hand in hand. And we found exactly what everybody says. If you can regenerate your solvent and keep that temperature in control and make sure that the contact is working, then you're going to minimize the majority of your problems with meeting specification. Some of these other ones, phase envelope. If your amine is colder than the gas, you're going to condense hydrocarbons out, so that can be problematic. Under circulating, that's a problem where you don't have enough amine into the tower to account for the quantity of H2S and CO2 that are in the feed gas. Amines cannot infinitely hold acid gas. They get full, like we do at a buffet. So if you don't pump enough amine into the tower, eventually it gets full, and whatever H2S has not been previously absorbed, it will pass right through the tower and go out with sales. Over circulating can actually be a problem. Many people, when they go off spec, the first thing they do is crank up the pump. I need more amine in the tower, but the problem with that is, as you increase your circulation rate, it increases the duty load on the reboiler. And if you don't account for it, you suddenly don't regenerate the solvent as well. So by over circulating, you end up in this high lean loading problem. So we have to, and also sometimes the coolers don't work as efficiently when the amine's pumping through rapidly. And under strength, you need to have a certain quantity of amine in your circulating solution to account for how much H2S and CO2 is coming in with the feed. So a couple of pictures, a few things. This was a plant that was supposed to make less than 100 ppm of H2S. It happens to be a refinery, but I can show you the pictures. They were actually processing at rates above 1,000 ppm on the outlet of the contactor. So obviously something wrong. We went through all the amine parameters. They were circulating the right amount. It was well regenerated. The temperature was good, and it's still not working. So what can you do to check? One of the things you can do is run a gamma scan, which we show in the top right corner here. Now, typically a gamma scan will show where every tray is. And if any of you have ever seen a gamma scan, you know that this particular picture shows that there aren't any trays in this tower. They're missing, or parts of them are missing. So when they shut the unit down and we went inside, all the trays had completely buckled. There wasn't a tray left in position. And so obviously if there's no trays, you don't have intimate contact between the gas and the liquid, and there's no removal of H2S. It did a remarkable job to take it from 2% down to 1,000 ppm of H2S with no trays, but we certainly don't want our towers to work that way. High temperature. This is we don't have this problem so much in Canada, but I understand there might be some Middle East people that have checked in here today, and where we do have ambient temperatures in excess of 45 degrees. It's a big problem. I took this picture at another plant in the Middle East, and this camel nicely stopped for me to take his picture. Heat is a problem. Although we don't like winter, amine plants run better in the winter than they do in the summer, because most plants, even in Canada, have cooling problems. As long as the plant doesn't shut down, it's not a problem. But obviously, if the plant shuts down when it's 40 below, people have issues. But our goal is to keep the amine as cool as possible. And we want that amine to be warmer than the gas. and we want to make sure that it's not too hot, so that when we get that chemical reaction, which is exothermic, and it drives the temperature up inside the tower, we don't want to have excessive temperatures where we can actually liberate acid gas inside the tower, because that can cause corrosion. So there's just an example. This is from simulation. But on the left-hand side here, this is a temperature profile inside an absorber. Now, typically we have a large temperature bulge at the bottom because we're reacting amine with lots of acid gas. We get a big exotherm. And then typically that temperature starts to cool down, and then it levels off as it goes to the top of the tower. In this case, we have a massive temperature bulge. Oops, a massive temperature bulge, way too hot. And on the right, we're showing the H2S absorption profile. Typically, this goes from the inlet H2S, and then there's a relatively rapid decrease in H2S, and then this levels off and goes sort of straight up the y-axis here. But in this case, you can see we're picking up a little bit of H2S, and then there's no absorption of H2S inside, 60% of that tower. And it isn't until the amine cools, again near the top, that we can actually get some absorption and removal of H2S. The problem with this type of profile is we're not using 60% of the tower, which means we're not on spec at this point. This is, 0.5% H2S in the treated gas. So that's clearly off spec. So temperature is a huge issue. This is a particular client that they couldn't meet spec. This is a CO2 removal facility. It's for an LNG facility. And they could not meet spec. When I ran the simulations, this is the simulated temperature profile. We don't like to have amines above 85 degrees C because they have the potential to liberate acid gas. And then obviously at high temperature, they also don't want to absorb CO2 or H2S. So they didn't believe the simulation. So we went out with a thermal imaging camera and we took a picture of the contactor here. And you can see it's white hot in many cases, which is more than 95 degrees, which matched the simulation. So when we have an extremely high temperature inside the contactor, it's bad for corrosion, it's bad for performance. But how do we solve that problem as quickly as possible? And the key is when we have an excessive temperature in the tower, we need to pump more cold amine into that tower to drive that temperature down and out of that column. So in this case, we have to raise the circulation rate by 20%. And the simulation predicted a typical profile where all the heat's at the bottom, few trays of the tower. We have a nice cool top of the tower, 40, 43 degrees, lots of capacity, lots of absorption. And then we went out and took the thermal imaging camera, and you can see that the simulation matched what the thermal imaging camera showed. Nice cool 40, 43 degree top part of the temperature, lots of final absorption, easy to meet spec, all the reaction at the bottom of the tower and at temperatures less than 85 degrees. So you can, if you have a simulator, you can predict trouble, and you can use a thermal imaging camera to make sure that you're actually seeing it. But these are all tools that you can use to improve performance at high temperature. So that's it for meeting spec. In the interest of time, we have to get on to corrosion. Corrosion has many aspects. There are three separate ones here. The first one here is galvanic corrosion. And what you're looking at, this is a regeneration tower from a plant in Alberta here. They could not regenerate the gas. Even though they had a high overhead temperature, the steam was getting to the top. They took the plant down, and on every single tray in the regenerator, there wasn't a single valve left on any of the trays. So the reason they couldn't regenerate is because they can't hold liquid on this tray deck because there's massive holes on the tray deck. And what you're looking at here, if you can see my pointer, there's a valve. Now that valve is a smaller diameter than the hole. Originally, that hole was a smaller diameter than the valve. The reason we got a galvanic effect is because we have stainless steel valves on a carbon steel tray deck. And wherever that valve lifted and dropped and rotated, it contacted the carbon steel and ate up the carbon steel. So it looks like somebody came with a hole punch and just made larger holes here, but that's CO2 attack. Very sharp defined edges, and this tower doesn't work because of corrosion based on really bad choices to put dissimilar metals on a single tray deck. Never use stainless steel on a carbon steel tray deck. This one was related to poor design of a reboiler bundle. This is also a plant in Alberta. And the reboiler bundles are completely chewed up here. As you can see, there's no steel left in many of these places. Related to failure to regenerate inside the regen column, and also really bad design on the reboiler. And this one is a tragic one. This is a regenerator column in a plant in the United States. This is the original thickness, and this is the thickness of the plant after 1 year of operation. It actually even punched holes in the side of the regenerator column. And this was caused by high heat-stable salt, aggressive heat-stable salt attack on the steel. A heat-stable salt is whenever I get a stronger acid than H2S or CO2 into my process, it reacts with the amine and it makes a strong salt, and the salt is non-regenerable. So we say it's heat stable. We can't break that salt apart. So it builds up, and because we're retaining an acid, it drops the pH of the fluid and the acids attack the steel. So many different ways that we can get corrosion. So what did our root causes say? The highest one of all was understripping, and also high lean loading. So 52 and 27, that's almost 80 of the total root causes were related to failure to properly regenerate the solvent. We cannot be leaving high H2S in the amine that goes down to the reboiler and in our lean piping, because a lot of that lean piping is hot. We have to remember that corrosion is a chemical reaction, and all chemical reactions proceed faster and more aggressively at high temperature. So whenever we've got acid gas and high temperature in the same place, we're just asking for trouble. We've got issues with design. I guess if we can go here, we can loosely put most of these problems related to design. We've got some operational issues, and we always have amine hygiene issues. How do we take care of that amine solvent? Do we build off a lot of heat-stable salts? Do we not filter it properly? Is it degrading because of temperatures of the way or what's coming in with our feed? Did we design the right metallurgy for the application? Did we overload that solution on the rich side? You know, did we not size the piping correctly? Is there vibration in the reboiler bundles, in the piping? Cold spots are an issue because wherever you have what we call a cold bridge, which could be a ladder to the side of a vessel, a manway, temperature probe locations, any of those can cool down the temperature of the regenerator or contactor, and that's a point where we get condensation. And if there's acids present, the acids condense in the metal wall and we have corrosion problems. So there's too many of these to go over, but typically, you know, it seems obvious if we can regenerate the solution properly, design it correctly with the right metallurgy, and make sure that we don't overload the solution with H2S and or CO2, that we can eliminate a lot of our corrosion problems. So this is a really interesting part of the database, is where exactly did the corrosion occur? And I'm going to start here at the bottom where it says system-wide 15. So out of these 131 cases, only 15 are what we would consider system-wide, which means, you know, there was corrosion in the reboiler and the absorber and piping, and it was all over. Like, not all from the same mechanism, but they had system-wide corrosion. Now, one thing you will note is that if you're operating a plant or you're an engineer in charge of that plant, corrosion is generally highly localized. You never go to a plant and a turnaround and see corrosion in every piece of equipment. Corrosion is very highly localized. So this number made sense to us. And a number that might not make sense to many of you is if you understand that H2S and CO2 are corrosive, and you look at an amine flow sheet and you say, okay, where's the most acid gas? It's right here, and it's right here in the rich amine solution, and obviously up here in the acid gas. But right here where the rich amine comes out of the bottom of that absorber and then into the tower, this is the most highly loaded part of that amine solution, yet it only has 9 corrosion events. And the ones on the lean rich exchanger were primarily on the lean side. So really only 5 events on this rich piping, and that's where we have the most acid gas. So how does that make sense? It makes sense because this temperature is moderated here. It isn't until we start to heat up the rich amine that we can have rich amine issues. So temperature is a key. Look where all the corrosion occurs: reboiler, regenerator column, bottom, mid, reflux, lean pumps, lean amine piping, coolers. What's common about all these locations is temperature. They have the least amount of acid gas down here, but they have the highest temperature. And temperature is always going to aggressively increase rates of corrosion. So as far as all that corrosion that occurs in the reboiler and the bottom part of the regenerator, the big driver of that is the fact that you have not stripped inside the column itself. You have to regenerate inside the tower, not in the reboiler. And why does that happen? The first case is insufficient steam traffic up the column. You need to have enough steam that you have a proper overhead temperature. You know, typically that's over 100 degrees C as your overhead temperature to the top of that still. You want to make sure that your lean rich exchangers are working, that you don't have temperatures below 90, 95 degrees C rich amine feed temperature. And you have to make sure that you don't have a high column back pressure. And the reason for that is the higher the reboiler pressure is, the higher the boiling point of the fluid, the harder it is to generate steam at high pressure. So our goal is to not have a high back pressure on the reboiler so that we can generate the maximum amount of steam that we need to regenerate the solvent inside the column and not down in the reboiler. Some glorious pictures of corrosion. This is a lean amine cooler. Massive attack. This is the bottom of a regenerator. You can't see all these numbers, but this is 0.225 inch pit on a 0.25 inch corrosion allowance. So we basically made our way 95% through the corrosion allowance. This was a 0.12 inch pit, and yet this part of the plant here, it's exactly the same width of steel as you had when the facility was built. So pitting type corrosion is dangerous because if you're not checking the right locations, you can put a pit in the side of a vessel before you're even aware that you've got corrosion going on. And how do I recognize a CO2 pit? Here's some classic CO2 pits in this thing. They're sharp-edged, round-bottom pits. So this is classic CO2 attack on the head of a reboiler. This is the reboiler bundle. This plant decided they were overstripping their solution and they were going to leave more H2S to build a protective film on the lean side. The problem with leaving more H2S in the lean is that you also leave much more CO2. So they didn't leave enough, they left more H2S, but not enough to provide a protective film, but all the extra CO2 that they left in the amine hit the reboiler and chewed up the reboiler bundle. So this was a catastrophe caused by poor decision-making on overstripping a solvent. And this is a pump feed, also corrosion. So lots of different types of mechanisms. Corrosion it's a 2-day course, easily 3-day course. So it's hard to talk about it all in short order. So what can we do to control corrosion? A big step is amine hygiene. Control your heat stable salts. One of the benefits we have in our natural gas industry is we don't tend to bring a lot of acids, strong acids with our feed gas. It's primarily just a hydrocarbon. So we don't generate a lot of heat stable salts. If any of you ever work at a refinery, we generate a lot because we generate a lot of organic acids when we do work on the crude oil that comes in. So we generate a lot of heat stable salts. Primarily in gas plants, we're dealing with degradation, and the degradation pathway is CO2 attack. H2S does not degrade an amine, CO2 degrades an amine. So the more CO2 you process, the more likely you are to degrade the solution. That's why many of us have gone to MDEA, because MDA is the most robust amine against CO2 attack, because there's no direct reaction pathway between MDA and CO2. We've got some loadings and velocity guidelines. We want to make sure that our solution is properly stripped. If we leave too much H2S or CO2 in our lean solution, then our lean piping can be corroded, and we want to make sure that doesn't happen. So some sort of primary, secondary, tertiary amine guidelines. Now these are guidelines, loading guidelines for corrosion, but you might have to go to lower lean loadings to meet specification. Just remember that. Maybe you need 0.001 mole per mole MDA to meet your sales spec. As far as the rich side goes, between 0.4 and 0.55, why such a huge spread? The lowest part, the 0.4 or less, is generally related to CO2 facilities or processes that are primarily CO2 removal. Because of the failure of H2S, no presence of H2S to provide the protective film, we tend not to overload a solution with CO2 because it's a very aggressive corrodant. If we're treating primarily H2S, we can push that rich loading limit to 0.5 and potentially 0.55 mole per mole. And we want to make sure our velocities are controlled in our piping. Less than 3 meters per second is kind of the industry guideline. And if you put in stainless steel, we can flow higher velocities. Max rich loading is kind of undetermined. There are plants that have pushed their rich loading to 0.75 mole per mole by putting stainless steel through the entire rich side of the facility, but that's sort of a corporate decision made by operations staff and engineering. So I wanted to include one final thing here in corrosion, that's hydrogen diffusion. We don't see a lot of it anymore because plants are built now with what's called HIC resistant steel, hydrogen induced cracking, HIC, H-I-C, HIC resistant steel. If you're going to build a new plant, it should be built with HIC resistant steel. The reason we're doing that is we're trying to control these hydrogen cracks that can form inside the steel. And I wanted to include this film. It's tragic, but it's the reason why we do post-weld heat treating on all our amine processes. NACE has recently relaxed post-weld heat treating on MDA and lean locations, but I leave that as a corporate decision on what you choose to do. So this is a refinery. It's not a gas plant, but it was an amine unit, MEA contactor. It was 14 years old. The operator, and about 5 years after service, they had severe corrosion in the base of the regenerator. So they replaced the bottom head of the contactor, sorry. They replaced the bottom head and they welded a new can at the bottom, a new sump at the bottom of the absorber column. And they didn't post-weld heat treat the weld that they did on the facility. So a few years later, they found more corrosion. They put a Monel lining in that bottom head, but the Monel lining didn't go up to the weldment. And a few years later, an operator was doing his rounds and he noticed a crack. And the initial crack that he saw was about 6 inches, whatever that is in millimeters. I'm losing my thought here, but say a 6-inch crack. And then by the time, so he tried to shut the gas down, cranking the valve, and he ran back and it had made its way almost to about 600 millimeters by that point, which is a very large crack. So they tried to evacuate as fast as they could. They brought in the fire department, and then they had a major release of gas, and whether the fire engines or whatever set off the explosion. But this video here is going to show you what happened here. And the root cause was a failure to post-weld heat treat. So there's obviously a massive blaze going on, but we're going to hit a point here that's right here. And you can imagine if there's people working in that area, the fire department. So 17 people were killed and a number of people were injured. This is a plant in Romeoville, just outside of Chicago. Union Oil Refinery. So this is sort of the onset of everybody post-weld heat treating. And the amine contactor, during that massive explosion, it blew 1 kilometer away. They found the contactor a kilometer away from the plant site. The bottom was still present in the blast zone. But this is a 1-inch thick, 25 millimeter thick column that completely shot off like a rocket. So always be careful. Remember, as a safety moment, we're dealing with flammable gas. Always be diligent. And finally, we'll talk about foaming here. Oh, I've got my grocery list here. No, sorry. This is here for a reason. This is a can of Gillette Foamy. It's just it's shaving cream. And I looked at the ingredients of shaving cream, and if you look at the top, there's water. there's amine. So triethanolamine is basically MDEA with an extra ethanol group. It's a tertiary amine. It's got hydrocarbons in it, and it's got organic acids. And then it's got things that, some fragrance, something to stop it from rotting inside the can, and another bit of a surfactant here. But everything in white here is exactly what you have in your amine plant. You've got water, you've got amine, you've got hydrocarbon. So everybody asks, how come my amine foams all the time? The reason is it's the base product for shampoos and shaving creams. All you need to do is get a surfactant in there, and you've got a foaming event that can happen. So what are the root causes of foaming? As expected, feed contamination is the big one. Your feed coalescers, your knockout drums, your filter seps, they're there for a reason. Never, never, never save money on inlet separation in a gas plant. You think you're saving money, and it's costing you operational dollars hundreds of times more than you would have spent on proper inlet separation devices. So a good large separator to handle large liquid loads, followed by a filter, followed by a coalescer is ideal. Reflux purge, we'll show you a bit about that. Ineffective flash drum. So if you don't control it coming in, you don't control the feed contaminant, how do you control it when it's in there? With your flash drum, your carbon beds, your filter systems, and your reflux, believe it or not, is a good way to eliminate foam promoters. What are the types of contaminants that can come in? The big ones in gas processing are compressor lube oils, pipeline chemicals. If you're doing corrosion inhibitors in the field, any kind of chemicals you're pumping in, a lot of those are surfactant heavy because they need to coat the pipeline. And another word for surfactant, when it enters an amine system, it's another S word, and that S word is soap. So most of these chemicals will turn amine into a soap if they enter your process. Solids don't cause a foam, but they stabilize foam. So any solids that can also enter the gas can cause us grief with the foam stability. So here's kind of an inlet separation. We like a large three-phase separator to knock out large liquid incursion, and then we like a coalescer. The coalescer traps aerosol mists down to, say, 0.3 micron. And if we can control down to 0.3 micron, we can virtually eliminate any carryover of foam promoting contaminants. It's nice to have a tie-in for a filter upstream of the coalescer to protect the elements. These are very expensive elements. Filters are a little bit cheaper, so we don't really want this to become a solid filter as well. We want it to coalesce. And it's nice to have a tie-in for a water wash, because sometimes you might not have a gas with enough liquid to properly get a coalescer to work. So if you can tie in a water wash to get some coalescing started, then these vessels work better. So foaming, this is an amine solution. We're doing a foam test, not that much foam. So, you know, our start level is there. And what we're taking here is, this is going to be a sample of, and I can't get this beautiful video to work. There we go. Get rid of my laser pointer. So this is inlet separator fluids, and we're going to pour it into the foam test, and bang. So you can imagine if you had a carryover of inlet separator fluids into your contactor, immediately that's going to cause a foaming event that's going to put you off spec and carry amine downstream into your whatever dehydration you have. So it's important to collect these liquids properly and don't allow them to enter your plant. And once they do, you need a good carbon bed and you need good filters. You should have the right filters. They shouldn't be black like they are on the left-hand side. And please change out the filters. This is a plant that we went to. They hadn't changed the filters in 3 years. They didn't realize they were supposed to. So you can see where all the elements were, iron sulfide everywhere. Filters are made to be changed on DP. Also, sometimes your filter material is incompatible. This is a fiber that was used in an amine filter. We took a piece of the fiber, put it in amine solution, ran a foam test, and you can see there's a very stable foam head. So whenever they changed the filters, the solution foamed. The vendor said the reason it's foaming is because our filters are so effective, they're pulling out your anti-foam, but really it was the filters themselves that caused the foaming. And this is a case of bad carbon causing foaming. This is lean amine feeding the filters. This is the lean amine after the pre-filter, and you can see it's about the same foaming tendency. And this is after the carbon bed. The amine foamed worse after the carbon than it did before. That's not what should happen. And then this is eventually the lean after the post-filter that was feeding the contactor. So because we went through filters, a carbon bed and filters, the amine foamed worse going into the filters than it did coming out. So make sure you're using the correct carbon. Don't use acid wash. Make sure it's a reputable vendor. Carbon can cause you grief. And I mentioned earlier reflux purge. The reflux is a great repository for contaminants. A lot of contaminants in your amine process are volatile enough that they might go overhead and then are recondensed. So they tend to concentrate in that reflux loop. And whenever you've got a foam that forms geometric shapes like here, pentagrams, hexagrams, foaming, as long as they're circles, they're not bad. But once you've got a geometric shape, that's a stable foam. So this is a reflux solution that we've done a foam test on. It's a foam that doesn't even break. So you can imagine every time you pump this reflux back into the top of your regenerator column, you're sending that all right back into the process loop. So most gas plants aren't designed to purge refluxes. Refiners do because they have ammonia problems. They need to get rid of the ammonia, so they regularly purge the reflux. But gas plants don't regularly purge a reflux, and it's a good thing in a design case or during a turnaround to, if you don't have a purge capabilities, to figure out a way to purge the reflux to some dump tank that gets trucked off site, because we need to get rid of these contaminants before they come back in the system. And finally, we'll talk a little bit about anti-foam. Anti-foam's obviously there to control foam. Try and keep your doses to a minimum. Anti-foams do not generally dissolve in water. They float on top. So don't use water as a means to dilute the anti-foam before injecting, and try not to overdose. So how do I know when I have a good anti-foam? The ones on the left are typically what we'll see: silicone, polyglycols, high molecular weight alcohols, and high molecular weight polyalkyl oxalates. Those are the big four that we generally see. And this is a proper anti-foam that should work in your system. So we've got quite a foam inside this particular facility. And we're going to drop some anti-foam in there. Probably could have done with just 2 drops, but bang, down to nothing. And that guy was in witness protection, so he didn't really want to be in the video. But this is what we expect to see from an anti-foam injection. Not only does it immediately kill the foam, but the foam doesn't return. If this doesn't happen in your plant, you don't have the right anti-foam for your facility. And that's something that you can check and test to get you the proper anti-foam. So in conclusion then, we've got key focus areas for why amine systems fail. What can I do? Number one, for spec, make sure our loadings, our solution is well regenerated and our temperature is under control. Make the amine slightly warmer than the gas temperature, but as cool as possible. Spend money on separation equipment, good inlet separation and good filtration with a high quality filter. Please consider also rich side filtration. Never underestimate the ability to remove solids from a system on the rich side. Do not understrip the amine. Do not be afraid to regenerate the amine solution. Too much of the world is worried about overstripping the amine, causing corrosion, when in reality, the majority of the corrosion is caused by a failure to properly regenerate the solution. And finally, keep your amine system clean. That means good inlet separation, good carbon beds, good filtration, skimming anytime you can, and control contaminants coming in. And that also means frequent analysis. Know what your solution quality is. So if you can control these 4, it says you'll have the likelihood of major system failures and probably closer to 75% control of system failures. So as an end here, we do have a paper available that this presentation is based on. It's called, this is the final version of it. We've got a number of copies, but the most recent is something called Trends in Tragedy, an in-depth study of amine system failures. where we show you the graphs and we discuss the points that are on all the tables there. And if you're interested in a copy, you can, here, I've got my email address here. Certainly feel free to ask for a request and we'll send you a copy of that paper. And we also have a YouTube channel, Sulfur Experts on YouTube, where we do little 10-minute sort of question and answers on these various topics. So that's it. I appreciate the attention. It went on for a while here, but lots to say, and thank you very much.
Okay, thank you, Mike. That was a good informative presentation. I'm still scratching my head over the shape of the bubbles, you know, circles versus geometric shapes, but let's get into the questions here. The first one came shortly after you started, and it's talking about the product quality category. So
Okay.
The question is, wouldn't product quality be a consequence from other failure types?
Oh yeah, and that's one thing I meant to say, but a lot of these failures are interrelated. So the big part of the database is what category do we put it in? And obviously if I've got, even corrosion, or if I'm foaming, I can't get contact, so I go off spec. So the question is it a foaming problem or is it an off spec problem? And really the foaming was the reason I went off spec. So we went with that as the focus. If you can control the foaming, theoretically the plant can get back on spec. But for sure, excellent question. Many of the problems are interrelated. So fix one, and because it's a cyclic process, that's the thing about it. If you make a change to location A, you're going to affect somewhere in location B in the facility. So you have to be aware that because it's a cyclic process, you can make changes and affect the whole process. So, yeah, good question, but yes, some of these are interrelated.
Okay, good. Moving on to the next one about gamma scans is, how does the gamma scan look if all of the trays are intact?
Yeah, I probably, if I had some room, I could have put one. So basically, I guess if I shot back to that gamma scan picture. Yeah, here we go. So we see the trays. See the trays on the right hand side. So the gray piece here is the column, and you can see where all the trays are. And then what happens is a gamma emitter is hung down the side of the column, and on the other side of the column is a device that collects the gamma rays. And depending on what's in the way of that gamma ray, a vapor is not going to give it much resistance. So we tend to get almost a return to the basically what our inlet intensity was of the gamma ray. Liquid is going to give you more of a something in the way of that gamma ray, so we get a higher deflection. And so on every one of these trays, you'll just see along this section here that's relatively short, it tends to go to about here on these elevations that we show here. So if the tower was working, these lines would process all the way to this part out here. And then finally, if you've got some foam, the foam is halfway between a vapor and a liquid, and it tends to put a little bit of a lump or a hump on this part of the gamma scan. So a proper gamma scan would look like this, only these would be extended depending on the density of the fluid that you're processing. And because the density is relatively consistent, the length of these peaks should be fairly consistent. So I don't know if I answered that question well enough. It's confusing, but we expect to see these lines only much longer. And then the vapor is returning back to here.
For sure. Now, do people do baseline gamma scans of their towers before they introduce process into them?
Yeah, that would be, well, you like to have process. So because you want to see how it's operating as a baseline with gas and with liquid flowing. But that's an awesome idea. It's all money, right? It probably, to do a single tower is $10,000 to come to site to do it. So it's an investment. But if you run a baseline, you can tell what the tower's, how it operates when everything's working properly, so that when you do have a problem and you bring in the you know, Tracer Co. or whoever does this type of work, you will scan and get a different scan than what the baseline was, and you can really help troubleshoot. The problem without a baseline is, you know, you're not 100% sure with the problematic one, you know, what's different about the way it should be. But it's a good idea to do a baseline for sure.
Okay, good stuff. Next question. I know you covered this a little bit, but based on your experience, would you say that the bulk of design failures are caused by the initial intent to reduce the capital cost of amine systems?
Yeah, there's two big problems. Number one, yes, capital cost. You know, you're trying to build a plant with the smallest possible. You're going to go to the bidder that has the cheapest quote, and he eliminates a lot of the bells and whistles. And a lot of those bells and whistles are important for operating. Things like temperature probes up the column, you know, correct differential cells, lots of gauges around the system, sample points, all things like that. So people are trying to save money, and that's the thing. And the other one, and it's probably even bigger, is the quality of the gas composition that the design was based on. A friend of mine, an ex-colleague of mine, had a great line. It was that there's one thing you can be absolutely sure about the design condition, and that is that the design condition is wrong. So the problem is, too many people see the gas composition, there's fat built in, there's things missed, and by the time the plant is designed and you actually flow gas to it, it's a completely different composition than the plant was designed on. And that's problematic.
Okay, good. Moving on to the next question there from a person that does a lot of foam testing for facilities. He says that he notices that a lot of new corrosion inhibitors have anti-foam added to their formulations. Will this reduce the risk to the amine user?
Yeah, I would say so. Anytime that you can get an effective anti-foam as part of a composition of a chemical, it's pretty rare that we have injection of corrosion inhibitors in amine system. I'm going to say that first. Amines in and of themselves in a process generally tend to be fairly non-corrosive, but so there are some plants that can't handle it with metallurgy, so they do put corrosion inhibitors in. And if you can get a component with an anti-foam that seems to work, then I guess it's good for you. The problem we have is it might not be an effective anti-foam for whatever's causing the problem. So it's kind of a wasted chemistry. But if it's effective for the plant, I'm not against it.
Okay, good. Next question. Why is continuous injection of anti-foam with reasonable dosage bad for the system?
Yeah, it's you're just introducing another chemistry to the process, and it depends on what type of anti-foam. Some anti-foams are designed for continuous injection. Those high molecular weight polyalkyl oxalates, they're actually designed for continuous kind of 10 ppm level injections. Some types of chemistries, like say silicones, they're not designed for continuous injection. So the problem we have is people are using an anti-foam that's not designed for continuous injection as a continuous injection mode. So as long as they do their homework and buy the correct type of anti-foam, you know, some plants, you know, in my long history, we just can't stop the foaming, and the only way to stop it is to add anti-foam. Or rather than continuous, there's lots of plants around the world that when the shift starts, the guy turns the anti-foam pump on for 5 minutes, and he controls the foaming during his shift, and he doesn't care what happens after to the night shift. But a lot of people do that. They'll just turn the pump on for 5 minutes at the start of the shift. It's not truly continuous, but it's certainly more than as required. Continuous anti-foam injection is like taking an aspirin every morning because you might get a headache that day. So is it, you know, it's good for your heart, I guess, but, you know, is it required? Maybe not necessarily.
Okay, moving on to some of the last few questions here. Usually a margin of 5 to 7 degrees is recommended for gas amine temperature. What's
Yep.
the maximum allowable amine temperature to the contactor, and does it go up with bulge temp?
Oh yeah, so great question. Sort of the rule of thumb is 5 to 7 degrees. There are certainly applications if you work in a facility with a tail gas treating system where there's no hydrocarbon in the tail gas, so we don't care about condensation of hydrocarbons. You might have a number of different feeds coming into a facility where your hydrocarbon dew point is lower than the feed gas temperature, so we don't really care that we keep a 7-degree spread. The temperature spread is basically designed to cover the removal of H2S and CO2 from the feed gas. Our feed gas is contaminated with H2S and CO2. And if we do a phase envelope and we find out what the hydrocarbon dew point is of the feed, it's going to be some value. And then as we remove H2S and CO2, we're concentrating the hydrocarbon. So the treated gas is now primarily 100% hydrocarbon. And that means that our phase envelope changes and it's going to shift down and to the right, which means the treated gas will condense easier than the feed gas. So we have to make sure that our amine is warmer than the treated gas hydrocarbon dew point. A big problem is a lot of people do hydrocarbon or phase envelopes on the feed. They don't understand what you really need to do is a phase envelope on the treated gas, especially if you have high H2S and CO2 in your feed. You're going to make a massive change in your condensation, your hydrocarbon condensation temperature. So typically 5 to 7 degrees is enough cover that you don't go below the hydrocarbon dew point. The maximum temperature is kind of like 50-ish degrees C for lean amine temperature. Doesn't mean it's not possible to treat with warmer than 50 degrees C temperature. It just gets harder. If you've got DGA is designed or its chemistry works that it actually does perform well at high temperatures. So that's a good chemistry for if you've got cooling problems. So diglycolamine. And the warmer your amine temperature, the warmer your bulge temperature is going to be. So that's another issue. If you have a lot of acid gas, you're going to generate a huge exotherm, which means the bulge in your tower is hot. The hotter your amine temperature is, the warmer the bulge temperature is, the closer you are to that magic 85 degrees C, then you're going to start regenerating inside your absorber, and then you'll have absorber corrosion. So I don't know if you understood that. Hopefully it made sense.
Okay, next question. What are your philosophies around the use of carbon beds online at all times or only when needed? And a follow-up question, what are the side effects of injecting anti-foam with the carbon bed online?
Yeah, great questions. You know, historically, the one thing is you should not have a plant where you don't at least have the opportunity to flow through a carbon bed at some point. So any filtration in an amine system should have a carbon bed. The carbon bed should be on the lean. The reason we don't put it on the rich is it's sour service. Plus, the rich tends to have a lot of hydrocarbon in it, so we'll use up the carbon too quickly. So the carbon, and it should be on the cool lean amine. Never put a carbon bed upstream of the cooler. The warmer the temperature, the less capacity the carbon bed has. So you're reducing it from say 13 to 15% active capacity down to 5 to 7% by running it upstream of the cooler. So the carbon bed is designed to remove organic foam promoters. If you've got a system that doesn't foam on a regular basis, it might be because you're flowing through the carbon bed, but it might also be that you don't need it. So it's nice to have it. We do have customers that run it 1 week a month or 2 days a week, and that's certainly okay. If you have continuous anti-foam injection, then it's almost silly to have a carbon bed in line because carbon beds will remove almost all the anti-foams that are used in our industry. And that means you're fouling the carbon bed with anti-foam and you're cutting its life dramatically. So if you're continuously injecting anti-foam, and anytime you do inject anti-foam, it's probably good practice to bypass the carbon bed for an hour or so, just so that you don't contaminate the carbon bed. So carbon beds are good. it should be online as often as you can. Just another thing, try not to exceed, say, 6 to 9 months of life with a carbon bed. Don't have it in service for 2, 3, 4, 5 years. It shouldn't be changed on pressure drop because it's all internal absorption that goes on. The reason we want it changed every 6 to 9 months is it's not only there for day-to-day removal of contaminants, but you really like to have access to a carbon bed if you get contaminant upset carryover from inlet separation. If you've got 1-year-old carbon, you don't have the capacity to get your plant back online. If you've got fresh carbon in there, you can maybe catch the problem before it puts you offline.
Okay. Next question. If a lot of places are less than 1,000 ppm inlet H2S, do you find they have trouble meeting the less than 4 mole to mole % rich loading in order to minimize the regen side CO2 corrosion?
Yeah, that interesting question. Some of these are long. Depends on your operating pressure. Like we mentioned, 0.4 or 0.55 mole per mole. If you're running a low pressure absorber, you know, 1,000 kPa or less, you can't even load the solution to 0.5 mole per mole solution. If it's a tail gas, you're lucky to load it to 0.1 mole per mole solution, or an acid gas enrichment facility, you know, maybe 0.2 mole per mole. So it all depends on what your equilibrium maximum loading is based on partial pressure. So what's your H2S and CO2 coming in? And if you have very little H2S and not a lot of CO2, you're not going to load that solution to 0.4 mole per mole loading or 0.5 mole per mole loading. So the question is correct. If you don't have H2S, primarily the rich is going to be CO2. So, you know, you just have to be aware. Maybe you need a little bit more stainless steel metallurgy in the hot parts of your plant, because the CO2 is going to be a more aggressive corrodant than H2S. So that's kind of an offline question. If you're interested in sending me an email, I'll answer it that way.
Okay, and since we're over time, we'll have one final question around process automation. And the question is, has anyone gone as far as doing online modeling to track everything in real time? And I guess maybe this question is around maybe HISIS or process control.
Yeah, plants that do dynamic simulation of amine processes. I don't really have the answer to that. You know, we certainly run spot simulations. I imagine there's technology out there to run continuous dynamic simulations to improve performance. I don't know that I see any of that in North America here. But that's a heck of a question. I guess it's data input, right? You need to have then you're going to have continuous gas composition of your feed gas. You need to have amine analysis done on a regular basis to know what your composition is. So you can do a reasonable assumption on what's going on a continuous basis, but you need to have data. It's garbage in, garbage out. So if you've got access to consistent acid gas or feed gas composition and amine composition, I suppose you can do some kind of dynamic simulation, but that's tough to do.
Mm-hmm. Yeah, I know, speaking on our side, from the producer side, we have process engineers that do that kind of stuff in HISIS, and I think they're just checking that what we're actually getting out of the system is consistent with what's in HISIS. So yeah,
it's mostly sort of photograph stuff. It's hard to make a movie out of a snapshot. Some people are trying to make movies out of a photo. It's tough to do.
Mm-hmm. And well, sorry everybody that we couldn't get to all the questions. I know there was a few more. If you wouldn't mind, you can email those questions over to Mike directly, and he can address them privately to you. And then again, I just want to thank everybody for your participation here, and be sure to check out the GPAC LinkedIn page for the upcoming events.
And thank you, everyone. Thank you, Gord. Thank you, GPAC.
All right. Thanks, everybody. Have a good rest of your day.